Welcome to the Tune Shop. We're going to be playing some tunes in the background. I got my partner Ziggy. He's right here. He's going to help with some math here. And today we're going to be doing problem number 15. 15 asks us to consider these two vectors and use the cross product to find and prove the identity stated below. Alright, and it also gives us that angle A, I'm going to call them A and B. I know they're Greek letters, but I don't know what Greek letters they are, where A and B, A is greater than B. So those are the things we know. Transfer them onto this piece of paper. This is what we're trying to prove. These are the vectors we know. A is greater than B. Alright, so before we even take the cross product of these vectors, it might be useful to point out that because this vector doesn't have a z value, it's 0, we can represent them in just the xy plane. We don't have to use 3 space here. And this is a very familiar setup. It's just a vector falling inside of a unit circle. Obviously, we don't know where that vector is pointing, but we do know it's going to be a unit long because radical cosine squared plus sine squared equals 1. And we know that because of the trig identity that cosine squared of theta plus sine squared of theta equals 1, and the square root of 1 is just 1. So that can be said for both vectors. What we do know is that vector u is going to have a greater A. The angle between it and the x-axis is going to be greater than it is for b. So that is one thing we do know. Alright, so that having been said, let's take the cross product. Here we go. So, take the cross product. I'm gonna write it out. IJK. Excuse me, sir. IJK. It's asking for the cross product here between the vectors. So it doesn't really matter which order you're gonna do it in. So we'll just do cosine of A and sine of A on top, cosine B, sine B on bottom. Alright, so that cross product, it's going to be, so because we have these zeros here, we know that the I value is going to be 0. And because we have the zeros here again, we know that the J value is going to be 0, which just leaves us with the K value. And that K value is cosine of A times sine of B minus cosine B sine A. And there we go. So that vector, of course, because of an identity of cross products, we know it's going to be orthogonal to both of these, which means that it has a z value and no x or y value. Now, how do we relate this to the information that we've already figured out in order to prove this identity? Because right now, this looks an awful lot like this. The only difference is that this is this times -1. So we're going to look at this. We're going to figure this out here. So you know that the cross product, one of our identities that we already know, is that the cross product between any two vectors u and v, if you take the magnitude of that, it's going to be equal to magnitude of u, magnitude v, times sine of theta, theta being the difference in angles between u and v, and in our case, because u and v are a and b, that can be a, because a is the greater one, minus b. There we go. And we've already taken the cross product right here, and to take the magnitude of that, because it's a vector where the x and the y components are both 0, the magnitude is just the z component. So, it's very simple. You're just going to take cosine A sine B minus cosine B sine A, and set that equal to this up here. Now, the magnitude of U, we figured out up here already. It's 1, and as is the magnitude of V. So, this can just be transferred as 1 times sine of A minus B. And now, you look up here, and you see that the identity is sine of A minus B. Well, we have that. Equals sine of A cosine of B. Well, we have that. Minus cosine of A sine B. Well, we have that. So, the only difference here is that this is that times -1. Well, how do you fix that? Well, no one knows. I don't know. I really don't. If I did, I'd tell you. It's just unfortunate. So the way we get the signs to switch on the left side of this equation is going to be to look at this cross product and realize that this is going to give us one vector, but that there's another vector with equal magnitude that faces in the opposite direction. And the way to find that other vector is pretty simple. You're just going to reverse all the signs. And when you reverse the sign of 0, it's still going to be 0, and same with this one, which means all we're really doing is reversing the sign of this one. So if you can just multiply that by -1. There you go, that's the same vector facing in the opposite direction. So then, when you look over here and you say, okay, well, we're taking the magnitude of this vector, well, now you're taking the magnitude of that vector in the opposite direction. And it won't matter because it's the same vector just facing in a different direction. So you can multiply that by -1 and get our identity up here, which is cosine of B sine A minus cosine A sine B equals sine A minus B. Boom!